Thank you, Aravinda. Thank you, Arul and Suhail, for putting together this very exciting workshop. It's a great pleasure for me to be introducing a collaborator, friend, and mentor to many of us in the Department of Physics at IIT Madras, and of course, all of us at the center, Professor Karol Życzkowski. So Professor Karol Życzkowski is currently a professor of physics at the Institute of Theoretical Physics at Jagiellonian University, Krakow, and he also serves as the director of the Quantum Information Center in Gdansk. Of course, I could give a very long and elaborate introduction, but in the interest of keeping it short, I think this is the kind of introduction that Karol prefers as well. Let me just say that he's a physicist and a polymath, because he's also the co-author of the square root voting system for the Council of the European Union. He is the co-author of a skiing guide to the Tatra Mountains. And of course, he has also co-authored a monograph on the geometry of quantum states, which most of us here are familiar with, even if we're unfamiliar with the other two works of Karol. So without further ado, let me hand over the floor to Karol, and he's going to today tell us about dual unitary, two unitary, and multi-unitary matrices. Over to you, Karol.
Thank you very much. Can you hear me?
Yep. Yes, we can.
Yes.
Great. And now I try to share the screen. So please let me know. Can you see my screen or not yet?
We can see already, Karol.
Great. So let me start thanking for your kind invitation to India. I already visited Chennai, and I will be very, very pleased to visit on site again. And I hope I will visit it once more. And now I take the privilege to talk to you from Poland, from Europe. So it's my great honor to be the first speaker during this first workshop. And as you see, the title looks like it has nothing to do with physics, only simple math like matrices, unitary matrices, and special kind of unitary matrices. I will try to define those notions like dual, two-unitary, multi-unitary matrices. But of course, we are doing physics, quantum physics, and I hope I will convince you, even though the title deals with only with matrices, there is a lot of physical contents in this topic. So what are we going to discuss? Of course, we are going to discuss some special subset of matrices, unitary matrices, and we assume that the size of those matrices is kind of not a bit special, because we assume that the dimension is, let's say, not a prime number, but a power of some number. Well, let D physically denote the dimensionality of a given subsystem, and K will be the number of those subsystems, and then the capital N is just the total size of the system. And then we can also analyze corresponding discrete structures in a finite Hilbert space relevant for quantum theory. For instance, those absolutely maximally entangled states Arul mentioned a while ago, which in this case, they deal with 2K subsystems, and basically the idea is that each subsystem is as entangled with other subsystems as it can be. So, wow, a simple motivation why we do it. First of all, I have to admit we do not fully understand these structures which are relevant for quantum theory. For instance, we do not even know for what dimensionalities, for what systems or number of subsystems such strange objects do exist. And then we wish to use those novel schemes to, for instance, design new classes of generalized quantum measurements, construct original models of quantum dynamics, and for some people, there is important relation to quantum error correction codes. By the way, I think if you have some urgent questions, something is not explained well, please do not hesitate to stop me and ask questions. It's also good for me to see that there's somebody in the audience who pays attention. Let me make a simple introduction to, well, standard quantum theory. If we have two subsystems, like you see, I have here two pens, I need to describe this object in the bipartite Hilbert space, let's say A and B. I have subsystem A, subsystem B, and of course we define separable pure states. They are just vectors in this composed Hilbert space with the tensor product structure, and entangled states are all states which are not of this form. Of course, as you can guess, if you take a random state, then typically it will not be separable, it will be entangled. And then the most known example of such a state is, of course, the famous Bell state, which you know it very well. It displays a very strong, not classical correlations between outcomes of the measurement, because if you measure, let's say, one subsystem, you can deduce or predict what is the outcome on the second subsystem. From a mathematical perspective, we can use any product basis in this composed Hilbert space. So I and J, it is just a product basis, and then any state can be written or decomposed in this basis. So G, I, J are just the coefficients, expansion coefficients. And here comes a simple piece of math, more or less like 100 years old. There is a Schmidt decomposition, which practically nowadays we would say we are going to use the singular value decomposition of this matrix G. Physically, we rotate basis ij, and instead of double sum, we have a single sum. And now this vector lambda is called Schmidt vector, and this is nothing else as a vector of square singular values of the matrix G. Now, this is the pure state. We can define projector and partial trace. So partial trace means I take bipartite system and I average over one subsystem, and then I look at the second subsystem, let's say A, if I average over subsystem B. And then this object is, of course, a positive state. GG dagger is a positive matrix. And the Schmidt vector is nothing else as the vector of eigenvalues of the state sigma. To quantify entanglement of this state psi, one can use, for instance, for Neumann entropy of this vector lambda, but for us it will be easier to use so-called linear entropy, which is very simple formula. It's just purity, trace sigma square, and we use expression 1 minus purity, which is equal just 1, and here is squared sum of Schmidt components or spectrum of partial trace. In short, if this partial trace is pure, it means that the initial state is separable. And conversely, if the partial trace is mixed, the initial state psi is entangled. The more mixed partial trace, the more entangled initial pure state. And of course, the Bell state here can be considered as the maximally entangled state. Why? Because the entropy of partial trace is maximal, because partial trace is maximally mixed. So it's very simple to generalize this notion for two qubits. So now D is the size of the system. So generalized Bell state looks like this. All singular values are equal. They are just 1 over D, because reduced state is maximally mixed. And this is true not only for this state, but for all other locally equivalent states. So locally equivalent means that the unitary dynamics act separately on both subsystems. We have here local rotation UA times another rotation UB. So it's easy to see that the state is maximally entangled if partial trace is maximally mixed. So it's proportional, this matrix G, look, will be proportional to be unitary because Gigi dagger is identity, rescaled identity. So practically you can say that state psi is maximally entangled if this matrix of coefficients after rescaling is unitary. So all singular values are equal to 1. And then for bipartite system, everything is simple. We expand the state in a product basis, calculate singular value of matrix G, and those singular values determine uniquely entanglement of the state. Is it clear right now? Are there any questions? Yes, so is somebody not sleeping yet?
Hello.
Yes, are you there?
Yeah, I had a question. Like in the
Good.
previous slide, you defined something called linear entanglement entropy. So I was wondering, in what sense is it linear?
Well, okay. In fact, this name is a bit strange. You are right, because here you have a square, you have a purity, but it's not. It doesn't involve logarithm like in the von Neumann entropy. And okay, in fact, it's you are right. You could call it Rényi Rényi entropy of order 2. It belongs to the family of Rényi entropies, and well, this is one of the names to differentiate it from the von Neumann entropy, which involves logarithms. And here we prefer not to use logarithm, but the idea is very, very similar.
Okay.
Thanks for the question.
Yeah.
Yes?
No, just a comment. Could it
Yes.
be that, lambda I, you could think about it as an average of lambda I itself? Just the purity, really.
Yes, yes,
And that
yes.
way
So
it's-
purity you can, exactly. Purity you can consider as an average lambda. Yes.
Linear function.
Thank you very much. Thank you. Well, anyway, for bipartite systems, everything is relatively easy, and we can analyze such systems without any problems. We know what to do. The situation is more complicated with multi-party systems, but first I will discuss quantum gates. So what is now a gate? For me, gate, if I have a simple system, is just a unitary matrix which tells us about dynamics of a single system. If I have bipartite system, like 2-pence here, I can tell that I'm going to apply bipartite gate, which is nothing else as a unitary matrix of size d squared. So now you see why we are studying unitary matrices. They are just gates, so they describe discrete dynamics in time. I already mentioned that if I have bipartite system, it is important to distinguish local gates, which are just analogons of separable states. So if I have a tensor product structure, which means that the dynamics are not correlated, then physically it means that the dynamics occur locally. There's no interaction between subsystems. And then all other unitaries, which do not belong to this class, are not of the tensor product type. They are in a sense, they describe interaction between subsystems. It will be convenient to introduce such a simple algebraic notion. If m times mu is a product basis, I have an operator, so it will be now expanded with in a 4 index notation. I have mu and n nu, and therefore I have here 4 indices. And the operation of reshuffling, denoted XR, are like reshuffling or realignment, means that I just exchange 2 indices, n and mu. So blue indices are exchanged. Sometimes it's convenient to use such a 4 index notation. Then I exchange those indices diagonally, mu and n. Why this is important for us? Because I mentioned already standard Schmidt decomposition of a state. But now I can treat matrices as, in a sense, states in the larger Hilbert-Schmidt space. So I can use the same Schmidt decomposition Now it's called operator Schmidt decomposition because I decompose not states, but operators or matrices. For instance, unitary matrices of size d squared. And now look, so D is just normalization, is a dimension, but basically the formula looks exactly the same. Now AI and BJ or BJ, they do not need to be unitary. Altogether, the huge matrix is unitary. Those AI and BJ, they satisfy orthogonality in sense of Hilbert-Schmidt. And the most important part is that this lambda is just the analogon of the standard Schmidt vector. Normalized like this, those numbers sum to 1 because I put here d square in front. But the key statement is that this vector lambda can be computed as vector of eigenvalues of a positive matrix U reshuffled times U reshuffled dagger, where reshuffled is defined here. So I will explain how it works, but you see now that the shuffling just reordering of the matrix operation is useful because it allows us to compute in a simple way Schmidt vector of such a arbitrary unitary operator U. And now it's easy to see that if U is local like this, then this vector is in a sense pure. It has only one component 1, all others are 0, so entropy will be 0. It's a very, very exceptional case. The other case is if UR is unitary, then all singular values of this matrix UR needs not to be unitary in general. This vector contains all numbers are equal to 1 up to rescaling, so the entropy is maximal. So now look, if this reshuffled matrix is unitary, then it means that the original U is as non-local as it can be. Because on the one hand, we have local matrices, and the other extreme is the case if all those Schmidt coefficients are equal, then the gate is non-local. In a sense, it plays the same role as Bell states, maximally entangled states. Here, for this linear entropy, the maximum is defined by this number. How? So to show how it works, let me start with a simple example, unitary matrix of size 4. But in fact, this reshuffling operation can be defined for any matrices. So here I take matrix of size 4, but now it's easier for me to work back on the standard notation. So now I have only 2 indices, but I can use 4 indices if I wish. And now look, this shuffling or reordering is a very simple algebraic structure. I take an entire block and I reshape it into a vector. So practically I exchanged blue entries here and green entries here. Why? Because if I take this block and I put it as a vector, then black entries do not change their position and green are exchanged. By the way, can you see my hand, my pointer?
Yes, we can see.
Very well, very well. So now look, this is as simple as that, and this reshuffling operation is involution. If you do it twice, you get this initial matrix back. But of course, this is a very strange, very, well, kind in a sense, brutal operation, this reshuffling. You exchange entries, but of course, if you start with a, let's say, unitary matrix, after this operation, it will not be unitary. If you start with a Hermitian matrix, it needs not to be Hermitian anymore because it's a strange operation. But now, look, if we start with a unitary matrix of size 4, which is localized only in those black parts. So I do not here, look, this is a very simple matrix. You will recognize it's a unitary. Here it's like almost up to a permutation. It is block matrix. Here is identity. Here is standard orthogonal rotation. But what is here crucial? That those non-trivial parts, theta, they belong to the black part. So after reshuffling, they do not change. So this matrix is invariant with respect to reshuffling. What it means? That reshuffled matrix is unitary, so it has all singular values equal to 1, or in this case 1/4. So the Schmidt vector is uniform, so the entropy is maximal. So this family of 2-qubit gates, in a sense, is very special, because for any phase theta, those matrices, in fact, they are orthogonal, they are maximally non-local. They are maximally non-local in the sense that the entropy of, sometimes it's called entanglement entropy, is maximal. By the way, let me only mention that if theta is equal to 0, then you have 1, and then what you see is the famous swap gate. So 1 here, 1 at the like sigma x in the center, and 1 there. And then those gates belong to the class of matrices which are called dual unitary. So I'm not sure, maybe you can correct me. I know that there was a paper by Bertini, Kos, and Prosen. I think Pavel is here with us. I'm not sure whether it was the first paper in which this name occurred, but anyway, it's used for last years very, very often in many papers, not only from Slovenia, but in many papers from Slovenia. But in short, such a gate is can be called dual unitary if not only U is unitary, but you are as well. So here you see this is a special case, because if U theta is equal to U theta R, so if U is unitary, so is UR. So this is even stronger requirement, and of course it belongs to this class. Why this class is important? Well, look, there's another important statement.
Excuse me.
In fact, theorem. Yes? There was a question?
Yeah, like I was like, it seemed to me that this reshuffling which you did, is it like the partial transposition operation?
Okay, but it's not the same. Partial transposition, you exchange other entries, but you are right, in partial transpose, I will mention partial transpose. You exchange also 4 pairs of entries, but you exchange them in the block. And here we exchange entries outside the block. So in short, it's a very similar transformation, but not the same. But you are right, a very similar transformation.
Okay, thank you.
So it's good to see that they are somehow related. Yes. So I will mention now the famous Cartan form of a unitary matrix. So here, well, in this case, I stick to the simplest 2-qubit gates. And the following statement holds. Any unitary of size 4 is locally equivalent. So here, Vj are local matrices. Here's one local matrix, let's say at the beginning, or here's at the beginning, here at the end of the action. So the statement is that any U is equivalent to such, locally equivalent to such a matrix, where here you have a e to, this is exponent of such a, let's say, Hamiltonian, which is very simple, like Pauli terms. So alpha are just phases, but they are somehow weights of the Pauli matrices which act on both parts. But of course, since this is an exponent, this is non-local part. So first and last is local, this is non-local, and interestingly, there are only 3 non-trivial parameters. Those alpha phases, they in principle go from 0 to 2 pi, but then you can choose them to be, for instance, from 0 to pi/4. There were many papers about this in around 20 years ago. I will mention a few papers by Sirac and collaborators, Sirac and Krauss, Barbara Krauss and Sirac and Dürr and others. And in a sense, you can choose a fragment of this cube. You have a cube or a torus, because all 3 phases go in principle from 0 to, let's say, 2 pi. But it happens that there's such a small object here, so it's a small fraction of a cube is enough in the following sense, that for any U, there exists a point inside this set that you can choose this vector alpha. It's sometimes called information content, such that U is locally equivalent to such a form. Now look, if all those numbers alpha are equal to 0, so this is this point, this trivially vanishes, and we have a local gate. Now you can easily recognize Here this is a C0 gate, here is DC0 gate, here is swap I also already mentioned. And now those gates, which are as non-local as they can be, they occupy this blue line and they correspond in this vector of phases to the situation if two phases are fixed and third one, which labels this blue line, is free. So in a sense, all those gates corresponding to those blue lines are as non-local as they can be, and they share the same maximal entropy. Sometimes it's also called entanglement entropy. By the way, here you see a red line, a trajectory. So we discussed in the paper with Mandarino and Linowski the following problem. If we raise V to some power, so take one action of U, second, third, fourth, how alpha changes. And we could show that dynamics is very simple. It's just like motion along a line, but there are reflections of those boundaries of the Weil chamber, and therefore what you observe is like a Billar dynamics. So for a generic initial position, this trajectory will somehow come arbitrarily close to any point, also to this blue line of non-local gates. Now, we know that if you have a local gate, it cannot produce entanglement. So you can think that, well, perhaps if you have a non-local gate, it will always produce entanglement. Of course, this is not true because swap gate, so this is swap, it exchanges position x, y, it transforms into y, x. It is maximally non-local, as we already know, and it cannot produce entanglement. So it will not change entanglement, and therefore there's another useful measure, entangling power, defined by Zanardi many years, also only 20 years ago, which basically is a very nice, simple definition. So it is, you start with the product state, you act with U, and you check what is the average entanglement if you average over all product states. So EL is this linear entropy like purity. So this is the more general definition. It explains the name entangling power because it tells us what is the power of this U to entangle initially product state. But Zanardi himself found that there is a nice relation. Instead of computing this average, you can basically find an explicit expression where E of U is now just related to purity of the Schmidt vector. So here is U times swap minus E of swap rescaled. And this is entangling power. But then it's also good to use another quantity, which is basically dual. In a sense, you see there is only difference in sign here. It can be interpreted as typicality. So in a sense, for typical, so random matrices, it will be close to 1 or 2, depending on how you define it. And then it's interesting to study entire set of all matrices, all gates in such a plane. So I was pleased to work on this project together with my Indian colleagues from Chennai, including the Chennai and the yes.
No, the small typo. I think in the G, the last E of S is a plus sign.
Yes.
Yes. Thank you. Yes, so I changed. Yes, you're right. It has to be yes. Thank you very much. Here should be plus, of course. Thank you. And here is a picture from this paper. So basically, we have here EP is entanglement power. Here is this typicality. And now at the center here, this dot means average. It's just average over this object. By the way, you can consider this as a kind of a shadow of this polyhedron I showed before. We can show that there are two bounds. The upper line corresponds just to those dual unitaries for which UR is unitary, and the lower line for which partial transpose, which you mentioned, is also unitary. So you could expect, well, in principle, those two bounds will cross somewhere here. However, for two gates, for two qubit gates, we cannot achieve the maximum entangling power, and this which is can be achieved is achieved for C0 or DC0. Here is like a strange cutoff. So blue line represents dual unitary. Those lower line represents symmetric family of matrices for which partial transpose is unitary, but those two lines do not cross. This is related to the fact that, well, some special states for two qubits do not exist. Basically, or maybe for 4 qubits, the space is somehow too small to satisfy all constraints. For two qubit system, this general picture looks similar. We have also those two lines, but here it happens that those two lines do cross, and there exists, one can easily localize this matrix, which is a simple permutation matrix. I will show it right away, which corresponds to the maximum of entangling power. By the way, here is magnification, which shows that the structure of the set is still not simple, but at least the corner here exists, and this is an important point, because this is a matrix which is dual unitary, but it satisfies additional property because partial transpose is also unitary. So here how it looks like. So this is a permutation matrix. And now, interestingly, of course, you see the permutation matrix. It's almost like a Sudoku matrix. Shows the positions that in each block, each column, each row, you have different positions of one. And the key property is that after partial transpose here, or after unitary, after reshuffling, those matrices are still permutation matrices, so they are still unitary. Therefore, the entropies are maximal. So here, let's make a short break. I will show you a picture from Krakow. So Arul was here, so he can assure you it looks more or less like this. So maybe at some point after COVID, you could possibly visit Krakow and maybe attend even a similar event in Poland. And now we go back to physics, but discuss now, we change the gears, we discuss now multi-parted states. So if I have, let's say, 4 parties, 1, 2, 3, 4, let me use like, let's say those 4 cards here to visualize them. Situation is more complicated because instead of matrix, I have a tensor. I have a tensor with 4 indices. And with tensors, it's much not so easy to work with, like with matrices. It's, for instance, this singular value decomposition for tensors. Well, in fact, it's not as simple. It does it exactly. It cannot be so simply generalized. And then if I ask a question, which state with n subsystems are the most entangled? The simple definition is the states are called absolutely maximally entangled if you choose, let's say, out of 4 subsystems, any 2, they will be maximally entangled for such a partition, for such a partition, and for such a partition. And this idea is, okay, I should mention there are many papers about them. I just quote some like Scott, Facchi, and from Italy, here paper from Belgium. And those states are important because they are related to many different things, to quantum error correction codes, to teleportation, and so on. So interestingly, for 4 qubits, there are no such states. There's important paper by Higuchi and Sudbury. They were first to observe and to prove that such states do not exist. Then those Italian papers, by the way, maybe you realize here one important name as authors of this paper. Whom I have in mind?
That's the Nobel winner of this year. Yeah.
So look, Giorgio Parisi not only worked on stochastic resonance, but he also worked on frustration in maximally entangled states. So now I'm very pleased we were quoting this paper a few years ago, but now I can tell you we quote a paper by Nobel laureate, which is nice. And then we can tell that also this problem was discussed by Nobel laureate. So he was wondering why there are no armor states for 4 qubits, and the answer is that the space is too small. There are too many constraints. But if you go to 4 qubits, they were already states found by Popescu. They look like this. They have nice term, and they correspond just to this permutation matrix I described before. So here is the state, and this state can be related to nice combinatorial structure, which is called orthogonal Latin square of size 3. So you see I have here cards. So the idea is to put 9 cards in such a way that in each row, each column, there's only 1 king, 1 ace, 1 queen of different colors. And now from this pattern, it's a very nice combinatorial pattern, you can basically, looking at the address, there are 2 digits, and the rank and the suit are 2 other digits. You can write down such a state, and then you can write the corresponding error correction code. Okay, so here is only a statement that such state can be written in the following way. Here I have multiplication modulo 3, but then I can rewrite this state using this matrix U, which in this case is of size 9 and has the following property. It gives us the isometry between any 2 chosen properties like rows, columns, suits of honors of this pattern, but also it gives us the implies that if you take 4 cards or 4 subsystems and split into 2 pairs, for any splitting, the states are maximally mixed. So in short, those in combinatorics, we know that for d equal to, there are no orthogonal Latin squares. They exist for d equal 3, 4, 5. And interestingly, for d equal 6, they do not exist. So this is related to the famous problem of Euler. If you take 36 officers of 6 different ranks, 6 different units, they came to a military parade, and you want to arrange them in such a way that in each row, each column, there's only a single officer of a given rank and from a given unit with a given uniform. And Euler was sure that no solution exists, but even he was not able to prove it. The proof was given only 121 years later by Gaston Terry. He was even not a mathematician, a French, let's say, lawyer. This happened 121 years ago. By the way, here's a nice toy which looks like almost a solution to the Euler problem. And as you can guess, this is only physical approximation, because you see the colors are different in each row. Heights pretend to be different, but somewhere there they are not different. They look to be different, but they are not. So it's a physical approximation. Of course, mathematically, the theorem is correct. Last picture from Krakow. And now, well,
Karol, just
yes?
a quick alert that you have 5 more minutes.
Yeah, exactly. So I already told you about armor states, so I will not discuss too much why they are important. They are important for many, many different issues. And then I will only mention that if I have such an armor state, they can be written in the following way by this tensor. If it's maximally entangled with respect to all 3 partitions, it means that partial traces are all maximally mixed. That it implies that this tensor is unitary for all possible reorderings. And this was called like perfect tensor in the famous paper by Pastavsky, Yoshida, Harlow, and Preskill. But if you consider this matrix U, it's of order d square, it's called two-unitary. Definition is simple. If reordered matrices UR and U gamma, so reshuffled and partial transpose, remain unitary. So you see, this two-unitary notion is stronger than dual. Dual basically requires only 1 constraint, and two-unitary 2 constraints for UR and U gamma. So now we, motivated by the problem of Euler, we tried to look for armor state of 4 subsystems with 6 levels each. So in a sense, the state, if it exists, could be written like this, where UAB will be a matrix of size 6 times 6 is 36, and it should be just two-unitary. So if we find it, it will be a matrix which maximizes the entangling power. If we act with non-entangled systems, they will be entangled as much as possible. And as I mentioned, such perfect tensors of two-unitary matrices are used in tensor networks for models of bulk and boundary duality. However, you can easily see that the space we need to optimize our entangling power is huge, because it goes like 36 square or -1. So in dimension 1095, it's really difficult to, if you do a random search, it's very unlikely you will be lucky and find a solution. So here I'm pleased to tell you about the numerical search performed by Swahil. So the main input came indeed from India. So basically you see here, those are some approximations to the solution. Why the approximations? Because for instance, here you see there are two pairs of queens of diamonds. And for instance, here you have two queens in two columns. So they are not solutions of the problem of Euler. And interestingly, if you consider the following procedure, it's like synchron-like procedure. So you start with a given matrix, possibly unitary, possibly not. You reshuffle it, you perform partial transpose. Now you use like polar decomposition to get the closest unitary. You get another unitary. So you can perform such a game in the space of unitary matrices. However, if you have no luck with finding the seed, the initial point, usually you will not find the solution. But Swahili was first who found the solution. Interestingly, if you start from one of those matrices, from the neighborhood of one of those permutations, you will not find it. So if you start from another one, you will find it. So Swahili was first who told us that such a solution exists. And then our colleagues did numerical cleaning. So they had numerical solution and they rotate the solution locally to improve the structure of this matrix. They found such a matrix. Then they realized that if they perform additional permutation, this complicated matrices, so here you have U, U, R, U, gamma, they can be taken to the block form of size. You have 9 blocks of size 4. Look, 6 times 6 is 9 times 4. This is simple. But here they have 9 blocks of size 4. And then if you check unitarity conditions, a miracle happens, because you can solve in each block unitarity conditions and find analytical expressions, and they are given in terms of golden ratio. So 1 plus square root of 5, and this matrix is complex, but here the key phase omega is the root of identity of order 20, which basically is related here to this circle. It's related to the golden ratio. And here, in a sense, now we see the solution of the problem. Instead of one officer in each row and column, we have 2 or 4 officers, which are in a sense entangled. But this picture corresponds to the matrix which we found. And in a sense, why this is interesting, if we show that such a state exists, and if we have a state in such a system in such a state, then choosing 2 subsystems, measuring them, we can predict what will be the outcome at other 2. So just to finish, multi-unitary matrices are similar matrices of size d to power k, which are defined in the following way: if after all possible reorderings, the matrix remains unitary, it's called multi-unitary. Here is such a simple example of size 2 to 3, 8, which remains unitary of all 20 possible reorderings, which means if you take 6 cards and for any choice of 3 out of 6, you get maximally mixed states. So I think I should finish now. So in short, strongly entangled multipartite quantum states are useful for many different applications. We are pleased to tell you, in a sense, mathematical theorem, that such absolutely maximally entangled states of 4 subsystems with 6 levels each do exist. And this solution implies solution of this quantum analog of the problem of Euler, finding the optimal bipartite matrix with maximal entangling power, finding the perfect tensor of such a size, and finding the new quantum error correction code. And in short, I think that looking for such extremal quantum states and corresponding multi-unitary matrices can be useful and applied in many different fields of quantum theory. Thank you very much.
Thank you, Karol, for a very interesting talk and for sticking to the somewhat tight time constraint. We have time for maybe a question or two. Maybe I could just ask you a quick question about the previous slide. You had shown this qubit. So that's a qubit system, right? You have a 3 qubit system, or is it a 3 qubit? Oh, it's a 3 qubit system. Sorry, no. I was wondering whether it was in some way related to the erasure 3 qubit erasure error correcting code.
No. So here it is just array of 6 qubits. So it is related to the code of if we have 6 qubits. But this is if we have 6 parties.
Okay.
So there are tensors which corresponds to the tensors with 6 legs, which are also very much often used in the tensor networks.
Indeed, yeah. Sorry, there was a question from. Please go ahead.
No, I was just saying that I mean, a locally connected 3-unitary will be related to 5 qubit error correcting code.
Yes.
Yeah, that's exactly.
Thank you.
Pointing out, yeah.
Yes, so I'm very pleased that I was having a chance to talk in your presence. Thank you.
Are there any other questions? There was one question in the chat. Maybe I can just read that out. I think this goes back to your very first slide. Can any Hilbert space in quantum mechanics be factorized into a product of 2 Hilbert spaces? Can any Hilbert space be factorized into a product of 2 Hilbert spaces?
Well, it's a more mathematical question, but it's a matter of choice. Because here, for instance, you have a complicated system and we assume it is composed of 2 subsystems. So in a sense, you can say, if you have a Hilbert space of non-prime dimension, you can artificially, mathematically speaking, assume that it is such a tensor product structure is embedded. But this is the matter of assumption, not of a proof.
Okay, so maybe with this we, sorry, Ayan had a question. Maybe Ayan, go ahead. Quick last question.
Yeah, I have a quick question. So I wanted to ask if there is some natural connection between this construction of this AME states and the entangling power non-locality with the complexity of the of this unitary gate.
So first remark is there are different constructions of AME states. We do not have a universal rule how to construct them, but if you find such an AME state, then you can show that this entangling power is optimal. So the corresponding unitary matrix, which is multi-unitary, it also maximizes entangling power. So there is this strict relation.
And about with the complexity, like how with this entangling power and non-locality generally. So by the I mean, could you characterize the complexity of the construction method? Like number of gates involved in this, total number of gates, minimal number of gates involved.
Good question. So here, now, to cut the discussion, I should say I don't know, but okay, we were working on it, but it is not so simple. It might depend on the particular case of the solution, yes? But a good question. Thank you very much. I think we should finish to ask another speaker.
Yeah, let's thank Karol for a really nice talk. And
thank you very much.
I think we have the next speaker of this session here.
Yeah.
Peter. Hi.
Yeah. Hi. Should I?